I keep intentionally switching the backgrounds and the patterns on my slides simply so they don't get boring. If I choose something that you don't necessarily like all that well, let me know, and I can avoid those types of things in the future. Unless they're just like colors of schools you don't like, then may not. All right, this is one where I actually do some calculations with this in calculations class toward the end of the semester. Not so much in pharmaceutics at this point in time, but it's an area that needs to be introduced. So kinetics of drug processes and with a focus on drug product stability. So there'll be some aspects of that in there, and we'll talk about some of the calculations that might be involved without necessarily doing a lot of those calculations at this juncture, because it's a little beyond the scope of the amount of time we have. But at least to make you aware of it, because when you pick up a product, and one of the first things you look at before you dispense it is the expiration date, right? You know, make certain it's in date. Well, where did that date come from? Where did that date come from? It's not like the least available quantity method where some scientists walked around and went, took it out of the air. Quantity, not quality. But to a certain extent, it may kind of seem that way. All right, so we'll look at this. The things we want to consider generally in this particular area. There will be a formulation. The tablet and capsule has drug in it. It's got a lot of other ingredients in there also. Some of those ingredients are in there to make it a tablet or a capsule, or even a suspension, or whatever type of dosage form it is. But there might be some ingredients in there to facilitate or help to make it a little more stable, to make it last a little longer period of time. Drug companies, as altruistic as it might seem, are in the business to make a profit. They can maximize their profit if the products that they make are stable for a longer period of time. And a later slide will expound upon this, but the target typically is if they can't make a product that's at least stable for 2 years, then the price margin on that is iffy. There are a number of products that aren't stable for anywhere near that period of time, especially some of the biological products, and they just kind of deal with that as best they can. But a tablet or a capsule, usually you see a 2 or 3 year expiration date on it. Pick up a container of aspirin. You might see an expiration date that's about 6 or 7 years down the road. They're stable for a long time. But if you open a container of aspirin and smell it, and you smell an acetic acid smell, you remember that smell from organic? Acetic acid is pretty distinctive. If you smell that, then it's degraded to salicylic acid and not usable. But usually aspirin is pretty stable. All right, so you got to consider the dosage form. So they're trying to make a dosage form that is convenient for a person to administer to themselves. More and more, that even includes certain injectables. There's a lot of injectables that people can administer to themselves. Factors to consider: nature of the illness, matter of treatment, age, condition of the patient. So really younger patients can't self-administer, somebody has to give it to them. Older patients might have some difficulty, etc. I'm not that old yet, so. And sort of peripherally, the type of patient. If it's an animal, then the animal tends not to be able to self-administer, so it might be put into a dosage form that makes it easier for us to give to the animal. If you're interested in animal pharmacy, I teach an elective on veterinary pharmacy that you can take in your second or third year when it's offered. And among the things I teach in there is how to give a tablet or a capsule to a dog and cat without getting bit and without them spitting it out. And it doesn't entail hiding it in food, because they can get smart enough and eat the food and shoot the tablet outside their mouth. Kids might do that too. So. There will be some studies that will go on long before the final dosage form is decided upon, and these are pre-formulation studies. Nothing novel about that particularly. But here you would study all of the attributes of your ingredients themselves. A lot of physical and chemical characterizations of not only the drug product, but also the excipients. So it's during these studies that you would decide which crystalline form of the drug would go into the dosage form I intend to make best. Which crystalline form would release the drug faster into solution, etc. So there are some choices that relate back to the structure that we talked about. Things that would be looked at are here, melting point, particle size, etc. We will have a section on microbaretics, which is the study of small particles, so we'll go into detail about that at a later time. But all of these things are examined, they're looked at, and sometimes it's a balancing act, like, okay, well, this crystalline form works best, but if it's this particle size, that works best in this, so there might be a compromise in there somewhere. So you can't have the best of everything, because those may not be compatible with one another. You may not be able to do them all at once. Solubility studies, dissolution studies, etc. So chemical kinetics. Chemical kinetics and pharmacokinetics have a lot of crossover. It's kinetics. Kinetics is the time study of something happening. In pharmacy, we're interested in what happens to a drug. At this point, if we're in a pre-formulation study, it might be stability. It might be degradation that we're looking at. At some point, when we get into testing in subjects, be it animals or people, then it would be the kinetics of what happens when the drug gets out of the dosage form, gets into the body, where does it go, how long does it take, how long does it stay there, blah, 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 all that's kinetics. All these factors, reaction order, reaction rate, rate constants, etc., in all those processes, all those kinetic processes, these relationships stay the same. What we're looking at might be different, but the mathematics, the kinetics itself, are identical. A first order process is the same whether it's in degradation or whether it's in distribution or elimination. Doesn't matter. The math describing that process is exactly the same. So you may see these things repeatedly, not just in this class and in calculations class, but in some other classes as well, in pharmacology and biochemistry. The interaction of drug at this receptor site would be described by these types of numbers. So reaction orders that are reasonable to see biologically and chemically for pharmaceuticals: 0, first, second, third order, pseudo order, Michaelis-Menten. Of these, the ones most likely to see, and the ones you'll see hit on more often, are 0 and first order, Michaelis-Menten, and pseudo order. A reaction may be a true second or third order reaction, but because of the conditions, it may give the appearance of being a first order or a 0 order reaction. Reaction rate is how fast the process occurs. Here the reaction rate factors greatly into how long a product is going to be stable for, based upon its degradation. The rate constant is related to the rate, but is not the rate. The rate constant depends upon, is a description of how the reaction proceeds under a certain set of conditions. Now, in chemistry lab or organic chemistry lab, you might heat a beaker up or something and you increase the temperature up toward boiling, this or that, and change the rate constant on something. In a biological system, the temperature and the pressure fluctuates very little. Blood flow has an effect on distribution of drug, but blood flow doesn't tend to vary that much. I mean, let's say you're going to have a supposition, well, what happens to the elimination of a drug if blood flow to the liver or blood flow to the heart goes to 0? Well, you can calculate the kinetics on that, but if your patient doesn't have any blood flow, I think you've got bigger problems. So though mathematically there are some extremes that you can theoretically look at, practically speaking, they never occur, or at least you don't care what happens to the elimination of the drug. You just want to get the patient's heart started again. It's a different issue. So the conditions are much more rigid, if you will, much less variable than you would see chemistry-wise. So from stability, rate constant might change. What happens to a bottle of tablets when it's exposed to an extreme in temperature? It's being shipped across Arizona in a non-refrigerated truck type of thing. That's an extreme that could change the rate constant. Biologically, don't tend to see a lot of change in rate constants, because temperature, pressure, all those types of things in the body, to have a viable biological system, you change that very much.
What's the pH?
Pardon?
pH.
pH can be a factor for some things. pH, in terms of affecting rate constant, doesn't necessarily change that. It might change the form of the drug and how it reacts in a particular process, but that process doesn't change. It can, but it's not as much of a factor as you might think. Stability-wise, yes. But again, we're talking outside biological systems. Types of reactions that we can see. I'm going to go through these fairly quickly. All right, so if you've got one reactant and several products, might be metabolites. And I'm going to go over that in a second. Metabolites can be active, can be toxic, can be inert. It's kind of a misnomer. A metabolite is supposed to be a less toxic version of whatever has been treated. So the appropriate term here is actually biotransformation product, but metabolism and biotransformation are used as synonyms by almost everybody. So the original meaning of the term metabolite has kind of been lost. So to the point that, strictly speaking, the term toxic metabolite is actually an oxymoron, because a metabolite is supposed to be, by definition, less toxic, but some terms get muddied. So this could be a reaction, or it could be a movement. So if we have drug in the bloodstream, it can go into the liver, it can go into the brain by some rate process that we can measure, by some movement. So all of these processes may not be chemical reactions, they may be movements. Yet the math to describe them is exactly the same. So your molecule may not change, just its location. So here this is saying because K1, K2, they're moving by different rate processes. And because it's a whole number greater than 0, then by definition, at least when I write it down, and in most places, fairly certain, this will be a first order. So this process of going from into the brain is described by the rate constant K1. First order rate constant, K sub 1. Series reactions, concept of a rate determining step. So if A goes to C, goes to B, goes to C, this could be different locations, this could be different metabolites. And if your ultimate concern is A going to C, whichever one of these steps is the slowest is your rate determining step. So the other step is almost, it's not that it's unimportant, but it occurs faster than the other step. So as soon as the other step occurs, then it's just there. So you may actually be able to simplify this by just looking at A to C and utilizing the smallest valued rate constant because that's the rate controlling step. Pharmacokinetically, you can look at pharmacokinetics in these 6 arenas. LAD-MER, Ladmer. And in many of these instances, I have written down which potential areas in pharmacokinetics can be described by these types of reactions. Liberation is it getting out of the dosage form. So it's got to go into solution before it can be absorbed. Absorption step, which may or may not be present. Distribution, where does it go? Metabolism, also biotransformation, is one of the ways that can be eliminated from the body. Excretion is another way. So the difference between those two is metabolism is the drug is chemically changed to something else, which may no longer be active, the remains of which may be in the body, but as far as we're concerned, the drug's been eliminated. Excretion is it's removed from the body still intact. Usually 2 organs do this, primarily the liver and the kidney. Most people think of the kidney first, but the liver can excrete things in the bile. And for a limited number of substances, the lungs could also be a spot of excretion. And then response. And all of these can be described by a series type of reactions and controlled by rate constant. So liberation, as an example, this is my drug in the solid state in the tablet, and the first step might be the tablet breaking apart or disintegration. And then once it's into a fine powder, then it would dissolve from there.
So liberation system.
Pardon?
Delivery system break down. Liberation.
Liberation is the drug getting from the solid into the liquid state in terms of pharmacokinetics. Because it's got to be in solution before it can get anywhere.
Liquid state or aqueous state? Liquid state or aqueous state?
It's got to be in solution. Doesn't matter where it starts, it's got to be in solution. Might be reversible reactions, movement into and out of body locations. That drug that moves into the brain, eventually it has to come back out of the brain to be eliminated somewhere else. Again, primary eliminating organs, liver and kidney. So absorption, distribution, metabolism, excretion, response. When a drug activates a receptor site, then eventually it moves away from that receptor site. So those are kind of reversible reactions. This may not, in some cases, we may not have a whole lot of control over these types of reactions, but again, we can measure them, we can mathematically determine. It's determining these types of rate constants and what's describing the reaction of interest that we could then use to calculate how much drug we need to give. Because if we calculate how it's distributed, in what fashion, and how it partitions into various and sundry organs, then we know how much drug to put in the dosage form, at least to start with. Eventually, it's going to have to be put in the dosage form, it's going to have to be put into a biological system. Typically for human drugs, they're tested in animals first. Unfortunately, the opposite is not true. For animal drugs, we don't first put them in humans. I think it'd only be fair, but you know, that's me. Combination reactions, series, reversible, irreversible, etc. So almost everything pharmacokinetic wise could be this. Might be chemical degradations, might be movements from one area to another, some combination thereof. So each of those arrows that had a K on it could be, we have to know what kind of reaction it is in order to do the appropriate mathematics. So a zero order reaction, A going to B, whether it's drug starting in area A and going into area B, or drug being form A and becoming form B. If the rate is by K sub 0, by definition, that's a zero order rate constant. So if you see this equal to some number, then by definition, that's a zero order rate constant. If that K has units of concentration as a function of time or mass as a function of time, it's also an indication that it's zero order. So if you look at the concentration of drug as a function of time, just straight concentration, and again, or it could be mass as a function of time. If that's a straight line on that kind of graph, just a regular rectilinear graph, nothing fancy about it, that's a straight line, that's zero order. So you see a straight line on a rectilinear graph, that's a zero order reaction. The slope of that line is downward because it's measuring a loss. So the slope mathematically is going to be negative simply because it slopes down. The rate constant itself, however, is not a negative number. Rate constants are always positive values. They're not negative numbers. Any negative rate constant has no meaning. You say, well, you get it from the slope, but the slope is only negative because it slopes downward. Rate constants are not. In pharmaceutics, to have something be a zero order reaction is desirable because it's much more controllable. It's not as quick. So this has come, here's an equation. If you take this is called a rate equation, so dA dt is equal to minus K0. And integrate that from T0 to T is equal to infinity. So the concentration at any point in time, so this could be C sub T, is equal to C0, the initial concentration, minus K0, which is the zero order rate constant, times time. So this is a zero order equation. So given the starting concentration and knowing the rate constant, then you can calculate how long it would take to get to some other concentration or amount. One of the values determined kinetically is half-life. Half-life, by definition, by whatever route, whatever mechanism, half-life is the time it takes to get from some starting concentration to half of that. It could be the initial, it could be somewhere in between, doesn't matter. But some starting concentration or amount to half of that, that's the half-life. Now, in a zero-order reaction, the half-life actually decreases with time, because the half-life depends upon how much is there. Because in a half-life, in a zero-order reaction, there's a constant amount, if you will, that is changed with time. So the time it takes to get to half of an amount goes down as the amount goes down. So if our concentration started at 0.2, the amount of time it takes to go to 0.1, takes this much time. But if I started here from 0.1 to 0.05, it only takes that much time. It takes a smaller amount of time, because there's not as much to start with. So this is another way to determine a zero-order reaction, is if half-life is not a constant. Half-life will actually decrease as the reaction or process proceeds. Unlike a first-order reaction, where the rate is proportional to the concentration, so my rate equation is dAdt is equal to minus kT. So time is a factor that's in there. The units of a zero-order rate constant are reciprocal time, so we don't see concentration in there. And the equation, when this is integrated from 0 to infinity, is log of C. Log of concentration is equal to the log of the initial concentration minus kT over 2.303. Now another form of this equation is the natural log counterpart. Because I often get the question of, well, where did the 2.303 come in? This is the conversion factor, if you will, between natural log, or log to the base e, and log to the base 10. So the log of the concentration as a function of time will give you a straight line. If that is natural log, then again, the slope is equal to the rate constant. If it's log to the base 10, which is what you typically see and do, then the slope is k divided by 2.303. So if we graph this like we did a zero order, we would not see a straight line on just a rectilinear, but we would see a curve. It would have to be log versus concentration. But the half-life, no matter where we start, the half-life stays constant because of that logarithmic relationship. So first order reaction, half-life is a constant. So if you have half-life as a constant, and probably a significant majority of reactions in the body can be described using first-order kinetics, which is why half-life is a useful biological value. It may even have attached to it biological half-life to differentiate it from a chemical half-life, but the math is exactly the same. Why is half-life a constant? Because the reaction rate is proportional to how much is there. unlike a zero order reaction, which has a constant rate. Now, what I did not say is the rate constant is proportional. I didn't say that. I said the rate was. Rate constant is constant. It doesn't change. So the K value here stays the same. Second order reaction has just the opposite. The rate of the reaction actually increases with the square of the concentration. So dA dt is equal to minus K, the second order rate constant, times A squared. That means there are two things that have to interact together. And as they interact and as they go down in concentration, then it's less likely for them to find each other to interact. So as you might suspect, if in a zero order, the half-life decreases. In a first order, the half-life is a constant. So in second order, the half-life actually increases as the reaction goes on. It takes longer to get to half as the concentration gets lower because your mathematical possibility of your two reactants finding each other to react goes down because they're less and less. So this is an equation describing that. So they're reciprocal kind of reactions. So the length of half-life increases as the concentration goes down because it's more difficult for the reactants to find each other. This is working under the assumption you got a true, so half-life is not a constant, but it increases with time. And this is working on the assumption that your two reactants are there in approximately similar concentrations. You can have a second order reaction if one of the reactants is water, and since our body is, like 70–80% water, though it's a true second order reaction, there's such an excess of one of the reactants that it actually gives the appearance of being a first order reaction, simply because one of the reactants is there in such excess. That would be a pseudo first order reaction. It's a true second order reaction, but when we measure it, it gives the appearance of a first order reaction. So hydrolysis types of reactions tend to be pseudo first order, and we would just do the math for first order. Yes, we realize chemically it's a second order reaction, but in reality there's such an excess of one of the reactants that there's no difference. So we don't see this relationship, we see it like a first. And that's what this describes. So because of that, the rate is equal to K times the two different reactants. But if one of these is there in such excess, then its concentration really doesn't change significantly enough. So the rate gives the appearance that it's our rate constant times just the smallest concentration of reactant, not the one that's in excess. So that's why it's a pseudo first order. So the math would just be just like a first order, and it would give the appearance that it would have a constant half-life. Biotransformations or metabolisms. So I'm trying to use those interchangeably because that's what you'll hear, even though biotransformation is the more appropriate term. Concentration of the binding sites, if they're much, much higher than the concentration of the drug, then it will look like it's first order. Key issue or points is if there are sufficiently low number of binding sites that they've become saturated, then it would actually give the appearance of a pseudo zero order reaction instead of first. So it looks like first order at low concentrations, zero order at higher drug concentrations. And it's not unusual for these, relatively speaking, higher drug concentrations to be in the therapeutic range. This is obviously more of a problem in overdose situations, because if all of the receptors are taken up and then there's more drug around, then that more drug goes around and sees what other mischief it can get into. Acetaminophen overdose depends upon this. When you get too much drug, the pathway that gets saturated from acetaminophen is one of the elimination pathways for a potential toxic metabolite. So when that gets saturated, then that toxic metabolite accumulates and results in irreversible liver damage. The treatment for acetaminophen toxicity is N-acetylcysteine. What that does is that increases the capacity of the elimination pathway of that toxic metabolite to try to help get it out of the system. So what happens when we're not at the extreme of a very high or very low concentration? We're somewhere in the middle. I guess, I don't know if it would have been appropriate or not, but we could put Malcolm in the middle, but it's not Malcolm. Oh, that does start with an M. So it's not zero order, it's not first order, but it has attributes of both. This is referred to as Michaelis-Menten. And you will encounter this quite a bit. This is Michaelis-Menten in their original publication, looked at the interaction with receptor sites in proteins. Drugs and proteins. There are also some reactions described in this fashion. So V is the rate of metabolite formation, PDT. Combine all these together, then this is the Michaelis-Menten expression. So the rate or the velocity, which is what the V stands for, of the formation of the metabolite or the reaction or the biological effect is dependent upon drug concentration and the affinity. So Vmax is the maximum rate when all of the sites are saturated. And Km is the concentration when the velocity is 1/2 of the maximum rate. So Km here, our Michaelis-Menten constant, in a zero order reaction, it has units, a rate constant has units of concentration as a function of time. First order, reciprocal time. Michaelis-Menten has units of concentration, because Michaelis-Menten is between zero order and first order. So graphically, you've got the rate versus the substrate concentration or the concentration of the drug. Then this goes up asymptotically, up potentially to Vmax. That's when we got all the sites saturated. So Km is the concentration when the velocity of the reaction or the speed of the reaction is 1/2 maximal. Km is referred to as the Michaelis constant. Only thing I could figure out is you had Michaelis and Menten, two guys that worked on it. They flipped a coin. It says, okay, well, you get to name the constant. It's probably not true. I just made that up, but it sounds good. Pseudo-order reactions, or we talked about a little bit, is reaction may be one mechanism, but based upon the conditions it gives the appearance of being something else. So one or more of the reactants is present in great excess would cause this. One of the reactants is a catalyst, so it doesn't change. One or more of the reactions are constantly replenished during the reaction, so it doesn't get used up. So these are reasons why you could have pseudo-order reactions. In enzymatic biotransformation types of reactions is the second one. It's a catalyst or a facilitator. It doesn't get permanently changed. It gets regenerated. Predicting rate constants. All right. Back a minute away from pharmacokinetics, back to stability. All right. How can you determine how long your product is good? You make the product, you let it set in a controlled environment, and you test it every now and then, and you do that over a period of 2 or 3 years, and then you can say, well, it's sufficiently stable over 2 or 3 years. Very sound scientific theory, but not practical. You need to get your product, if you're the company, out on the market as soon as possible. So to wait 2 or 3 years, just waiting to see if it's stable for 2 or 3 years, you would lose too much money. So what can be done is based upon the kinetic relationships that we have been looking at and measuring the reaction, then we can simulate 2 or 3 years. By increasing the temperature involved in the storage conditions, we can do an accelerated study. So we can measure 2 or 3 years worth of aging in a period of 3 or 4 months, simply by elevating the temperature. If the reaction is such that when you change the temperature to a certain extent, it just increases the rate constant, so now we're changing the condition, so we're actually changing the rate constant. So we're changing the rate constant at various temperatures, then applying the appropriate mathematical transformations, we can take those rate constants at varying temperatures and extrapolate it back to the rate constant we would see at room temperature, and from that then calculate the expiration date. And the FDA allows, this sound scientific principle, the FDA allows companies to do that. Now, as they put their product out on the market, they keep samples for 2, 3, 4 years. They're selling the product as they go along, so eventually they can verify that accelerated data with real-time data. But they don't have to wait, especially that first time, for real-time data and have a product ready to go and approved and not be able to put it on the market because it can't verify a 2 or 3 year expiration date. That's why for some of you that may have worked in pharmacies, you may occasionally get a letter that says, well, based upon our long-term studies, we have determined that our original accelerated 2-year expiration date wasn't enough. So your product actually has another year on it. So you may occasionally see information like that. You may occasionally get in the reverse. Well, we thought it was going to be 3 years and we found out it's only 2.5. So sometimes it happens the other way too. So the Arrhenius equation is based upon the reaction, and the reaction is described by a couple of main terms: energy of activation and this frequency factor. Frequency factor is kind of like a constant related to a particular reaction that's occurring. And then in here is the molar gas constant, which is a constant, but also the temperature. So by increasing the temperature and then measuring the reaction, then extrapolating that back to room temperature, you can guesstimate what the shelf life is going to be. So energy of activation for most drugs is somewhere between 12 and 25 at 25 degrees C, so 10 to 30 or so. This equates out to another indicator called a Q10 that we'll look at in just a second. So the energy of activation and the Q10 is a constant for a given set of conditions. Here, stability, pH, certainly can be a factor, an important factor. So you would want a pH where it was more stable rather than left. And it may be different at different temperatures. So the higher the energy of activation, the longer the shelf life of the molecule. Because the more energy that takes to go in to cause it to degrade, the less likely it's going to degrade. This is the amount of energy needed to get that reaction really going. Q10 calculation is based upon sort of fractions of 10 degrees. So it's looked at in 10 degree little increments. So a way to estimate the effects of 10 degrees C rise in temperature on drug stability. Similar concept to the Arrhenius relationship in that we're increasing the rate constant, and the rate constant only as a result of increase in temperature. So we're aging it faster, if you will. That's what an accelerated study does. So estimating the Q10, obviously this is the equation that I expect you to memorize and utilize on the exam. I'm kidding. Any equations I expect you to know, I will tell you at the time. Most of these, but you can see the relationship. Energy of activation is in there, molar gas constant, temperature. So some of the same things that we see in the Arrhenius relationship. Really the foundation of this is the same. Values tend to be 2, 3, and 4, and that's what with that original Arrhenius relationship, energy of activation, showed the corresponding Q10 value. So as the value of Q10 goes up, the more stable is the reaction, the longer the shelf life would be, because the energy of activation is actually higher. So the lower the Q10, the more stable the molecule in an elevated temperature situation. So the larger the Q10, the shelf life will be shortened, and that's just exactly the opposite of what I just said, isn't it? Let me double check that. That might be backwards. Let me double check that one. So stability testing. This is one of the things that would actually be started in pre-formulation testing. Stability testing. For everything, the drugs, the excipients, and the formulations. Long-term testing, 25 degrees, 60 degrees relative humidity for at least 12 months. Excuse me. Short-term testing, less than 6 months, accelerated, 30 to 40 degrees at higher relative humidities. You're trying to stress it, age it faster. Climate zones depends upon the conditions. So where you're going to sell it makes a difference. So whether it's a temperate climate, which is the white areas here, subtropical. Interestingly enough, the United States is considered by and large subtropical. Those of you from Michigan or Maine will look at that and go, say what? But maybe if you're from Florida or Texas, not so much. And then dry conditions. So depending upon what part of the world the product is selling, your accelerated stability studies may be different, or you may have to do multiple number of them. That's just to give you an idea of, it's not as easy as it sounds. Signs of degradation are specific for each dosage form. So appearance, color, strength. If something physically is obviously changed, then there's something potentially chemically wrong. Here's a thermogravimetric approach, and when this curve starts to go down, it shows degradation. So you can look at the standard product and the product after it's been stressed. Desired, mentioned this before, they want at least 2 years, can be extended when you got long-term data. More difficult to determine for extemporaneously compounded products, and we'll talk about that at a little later time. Typically your target, if it's still got at least 90% of the label amount in it, then it's still usable. Once it falls below that, it's not. There are some exceptions for this. The penicillin's one of those that when it gets below 100% of label, it's considered expired. So those tend to start with greater than 100%. In compounding, typical expiration dates, 6 months for solid or non-aqueous things that don't have water in it. If it's got water, 14 days unless you have other data to tell you, 30 days for other types of formulations. And there are some data sources for that. We'll have to finish this next time.
On the shelf life slide, you're talking about